So that kind of covers the configurations, both compression, tension, in each capacity load cells, and then 3-point bending with the lower capacity load cell. Are there any questions so far?
Can you tell us a bit about the optical extensometer?
Sure thing. Or actually, let's do a brief run through of the software, and then we can kind of expand on that. But just briefly tying into what you were asking about, the optical extensometer, it's called TRVX. It rotates into position and out of position. It views the sample at a 45-degree angle, or 45-degree normal to the frame. The top load cell is set up such that when you put in the upper fixed joint, it is oriented in that fashion. We do recommend the fixed joint for the optical extensometer. The main reason for that is the readings of the optical extensometer is affected by the field of view, and with the articulating universal joint, sometimes that field of view can change, or depth of field rather, sorry. And essentially how it works, I'm not sure where the markers went, but the camera views the sample at which you either affix little diamond markers or you kind of mark yourself. And it looks at the contrast difference between the mark and the rest of the sample itself. So if you are testing dark samples like carbon fiber, use lighter marks. If you're using lighter samples like maybe an aluminum or maybe, maybe a light ceramic, you would use darker marks. The camera is already aligned and calibrated. In addition to the camera, and we'll go over the controls in the software, you have a lighting system that can either increase or decrease your contrast. And this will all be a little bit more clear once we kind of go through the software.
Is this like image correlation?
It's similar, but it's not the same. And if you are interested in DIC, you can buy a module that can output the information from this camera to DIC software. But it is very similar where so with DIC you have a calibration standard where you calibrate the camera. There's the same calibration standard with the TRVX as well. This is a known standard with marks on it of known distances. And essentially what it does is it creates a pixel per millimeter correlation. So if you know in real life what the distance is between these markers, and you tell the camera through the software how many pixels it is away from each other, it creates that correlation. And that's essentially your calibration coefficient for this. And that's really similar with DIC, where you're looking for the displacement of your speckle pattern. So as opposed to DIC, where it's in any direction and you can get those strain fields, this is kind of unilaterally, either up and down, or you can measure your width as well.
So how does it compare in resolution with DIC and traditional extensometer?
Well, it depends on your sample size and your camera, your lens power. We have a chart that I can give you that can tell, depending on the lens power and your sample size, what class of extensometer it falls in. Similarly to how DIC is kind of affected by how small of a speckle pattern you have. That kind of affects the resolution of your DIC sample as well.
So this won't provide local data, right? It won't look like this won't provide local data, right? Localized data. It will just give you from point to point.
It's point to point. It's wherever you put your markers. So you're not going to get necessarily strain field data from it, but it will tell you the displacement of those markers with respect to each other. Or with your width as well, it looks with the contrast of your sample in the background to see the shrinkage of it as well.
So what's the size of the markers?
There's two markers. One is about this size, and then we have smaller markers too. I think they should be right here. So we have two separate size diamond patterns. Whereas the larger diamond patterns would be used for a camera with a large field of view, where you're expecting a high elongation, somewhere in the order of larger than 300%. Where if you're looking at small elongations, you would use the smaller diamonds.
What about compressions?
We don't really recommend the TRVX for compression, so it's mainly to tension.
Is there any extensometer that can help us with this compression?
Compression. So we do sell a deflectometer that is kind of a cantilever arm that attaches to the compression plates, and we also have an LVDT system as well. So if you're going to want to do that with your articulating compression plate, I would suggest a LVDT system. Essentially, it's two LVDTs on either side that kind of balance themselves, so you get an average displacement. I would say, depending on what type of resolution and the ultimate deflection of your sample, that what you get off the compression plates themselves, which is read by the crosshead, is pretty good. But we do have solutions for measuring deflection at a higher precision.
So if the deflection that comes from the instrument itself, if you're, say, compressing a metal that has very high strength, in that case, do we have to worry about the compliance of the machine to correct for the deflection, to correct the deflection?
So there is a software feature in there, and this is probably a good chance to transition to software, where you can kind of create a compliance correction baseline that can subtract that machine compliance from your compression test.
And is that like we have to do it physically, or is that already known, the compliance correction factor?
You do the compliance correction run initially, and then you can apply that compliance correction factor to subsequent tests.
Like, what's the order of the error in that when we, like, say, compress steel or something?
I'd have to look that up. All right, so I'm going to kind of clear space a little bit.